Okay, thank you, Peter. So thank you for the introduction. So yeah, my name is Henk, and this is joint work with Peter and my promoter at KU Leuven, Thias, and great PhD student Bout Piesens. And so this work is entitled Table Constraints for Integer Programming, and in it we're going to tackle table constraints using integer programming solvers. So to give some context and motivation, we have some solver-independent modeling languages like Minisync and CPMPy, in which you can express a CP model, and then we can solve it in a variety of ways using different backend solvers. So you can use CP solvers or set solvers or IOP solvers. Now, while IOP solvers are a very popular choice and can work very well for certain instances, because they are very well developed, tools like Gurobi. We can still see that if you look at the CP benchmark set, like the XCSP competition, they lag behind. There's a performance gap against a native CP solver that is state of the art, like CP set. And I believe there's at least two reasons for that we can tackle in the presentation of today. The first reason is that certain important global constraints, like table constraints, are not linearized as well as they can be. And the second reason is that we are not using the full IOP toolset that an IOP expert would use to solve the problem at hand. And by addressing these 2 points, we can close that gap at least a bit. So the important global constraint of today is the table. So we'll be totally focused on a table constraint. Table constraint looks like this. We have 2 arguments. We have a list of variables, and then we have a table. You can see here at the bottom that this table has 3 columns, 1 for each variable, and then it has 5 rows. And what this table enforces is that these 5 rows are the exact solutions that the variables can take. So the first row says, okay, x has to be 2, y has to be 1, and z has to be 1 as well. And that is a solution, but 2, 2, 2 for those 3 variables would not be a solution. And this is a very important class of constraint because it allows you to basically enforce explicitly arbitrary relationships. It's also used when we take an existing constraint and turn it into a table using auto-tabling. And for us, very important in the XCSP competition, if you look at all the thousands of instances that are available, 25% of them will have exactly this type of table at the root level, of course, just like this. And then there's even more instances that will have variants of it, or that will have the table as part of a decomposition. So it's a very important constraint. When you want to use an IOP solver to tackle this constraint, you have the problem that an IOP solver will not support natively the table constraint. Because at the core, an IOP solver only supports linear constraints. So the types of constraints you can see on the screen here. So what we need to do is we need to take the table constraint and represent it by a bunch of linear constraints that enforce the same relationship as the table does. A standard way to do this was proposed by Beloff et al., and which is the default currently in Minisync. And it works as follows. It creates binary variables, R of I, for each row I. When I say a binary variable, that is an integer variable with a 0-1 domain. So it's basically the IOP version of a Boolean variable. So it can be either 0 or 1, or false or true. For the meaning of each of these row variables is that if a certain row variable, like say the ith row variable, is true, if and only if that particular row is chosen. So we need to add, after introducing these new variables, we need to add the constraints to make that hold. For that, we need 2 types of constraints. The first constraint, which you can show here, it takes all the r's and it sums them together and says that they have to equal 1. This ensures that exactly 1 of the 5, in this case, row variables is true, and all the others are set to false. And this forces the solver to pick just one of the rows, exactly one of the rows, and not none of the rows or multiple of the rows. So now we basically, by just adding this first constraint, we have forced the solver to choose one particular row, right? Now, once the solver has chosen, quote unquote, a row, we need to ensure that every variable takes the value of that row. So let's say that the first row is chosen, then x should be 2. So for every column, and in this case, the second constraint is for the x column, we say, okay, 2 times R1. Now, R1 will be true if the first row is chosen. So we'll have a term there that says 2 times 1 or 2. And all the other terms will, of course, be 0. That's what the first constraint was doing. So we'll end up with x equals 2. So that works out. We will call this the integer encoding, and it's the most basic way of encoding the table. Now, alternatively, we also have a Booleanized encoding proposed by Thierry Petit. And it's actually based on the integer encoding from the previous slide, but before it applies that integer encoding, it will first Booleanize the variables and the table. With Booleanizing, I mean that it takes an integer variable and it introduces a binary variable for every domain value. So in set, this would also be known as a direct encoding. So let's say that x has 4 domain values, then we will also get 4 binary variables. And then the semantics behind every binary variable, let's say the j binary variable, is that it's true if and only if the integer variable x is equal to j. So this is the relationship that we want. To enforce this relationship, after introducing the binary variables, we need to add more constraints. They will look very similar to the row constraints we saw previously. It's a very similar idea, but now for domains rather than rows. So the first constraint again enforces that exactly one domain value is chosen. X can only be 4 and not 2 and 4 at the same time, or no domain value at all. And secondly, whatever domain value is chosen, so let's say j is chosen, then this will be 1, then x has to be equal to j. So you can really recognize the previous constraints in this Booleanization of x. So this has now Booleanized x, and this can be actually very useful in the rest of the problem when there are other constraints that have to reason about x being equal to j. And this is very likely to occur if there is a table constraint with x in it. So that is one of the advantages of doing this step. Now we also need to Booleanize the table constraint. So we have our original integer table constraint on the left, and then we Booleanize it to a new table constraint on the right. And you can see that's become a lot wider. This is because every integer column has been expanded into multiple binary columns. And we can also see that all the cells, they have gone from integer values to 0, 1. But it's still the same table. It will still enforce the same relationship, only now on the binary variables. So when x is 2 in the original integer table, in the binary table, we will see 0, 1, 0, 0. That basically says, okay, the x equals 2 binary variable has to be set to 1, and all the others have to be set to 0. So you can see these two tables mean the same thing. The binary table is still a table constraint, which is why we can just apply the integer encoding from the previous slide to finally truly enforce it. Now we get to our main contribution on the encoding side, for which we will add 2 additional steps to this pipeline. So what we will do is we have our integer table. We'll turn it into a binary table as just described. So you get the T with the B. And then we turn that into an MDD. So there's an additional transformation step. And this MDD, this is a multivariate decision diagram. This is another type of constraint that can express arbitrary functions. However, it can be much smaller than the original table. Let me first show you what the MDD does. An MDD is a directed graph. In this case, it's structured from left to right. The idea is that any path through it represents a solution as long as you assign the variables on the edges that are on that path. To explain that, let's look at one particular path through it, right? So this one. So this path represents the solution 1, 2, 3, which is also one of the rows in the table, which is why there's a path for it. If it does not appear in the table, there will be no path in the MDD. So you follow this path like this, and you can see that, okay, this edge, first edge will set x equals 1 to true, second edge will set y equals 2 to true, the third edge will set z equals 3 to true. So this MDD, the semantics of it enforces the same thing as the table here. We can see another path here for 4, 3, 3. And this is an interesting one because it shows why the MDD can be exponentially smaller. Because this one first sets x to 4, then y to 3. However, then it meets the previous path in a shared node. And this is because the MDD construction process and what's known as reduction has figured out that if you look at the table, whether you do 1, 2 or 4, 3, at this point you're in the same situation. Z has to be equal to 3, which is why there's a shared node for it, from which there's only one edge, namely Z equals 3. Okay, now we have an MDD. However, an ILP solver will also not accept MDDs. Again, at its core, it's only accepting linear constraints. So we still need to take the MDD and turn it into linear constraints, which is what we will do next. For this, we have a flow-based setup. So now we will take our MDD, and in a final step, I promise, we will think again about this MDD as a flow problem, from which one unit of indivisible flow is coming from the source node and is going to end up in the sink on the right. For that, we will add constraints for the source and the sink. And then for every internal node, we also need to ensure that if a unit of flow is coming in from any incoming edge, then the outgoing edge should also be designated to have 1 unit of flow in it. So the first constraint we add for that purpose is to say, okay, 1 unit of flow is going to come out of the source, which is going to set one of the outgoing edges, so those 4, to true. That's what this first one does. So now either x1 or x2 or x3 or x4 will exactly one of those will be activated as having some flow. Then we have to go through every node. So I look at this one in particular. And we can see that there's one incoming edge, the x equals 1. And if that one is true, then, okay, the flow can only go to one other edge, the outgoing edge of y equals 2. So that one should be set to true. However, we cannot just write, okay, x equals 1 equals y equals 2, because y equals 2 also occurs at the bottom here, at this edge. So just because this edge has some flow does not mean that y equals 2 has some flow, because it could also have some flow because of this edge. Instead, we need to add an auxiliary binary variable, again, for this particular edge, which says like, okay, it's not just any y equals 2 that has some flow, it's because of this edge. So that's why there's an additional binary variable here, and those are all the e variables you can see all over the place. Then we continue. So here we have another example where we now have a node that has 2 possible sources of flow. So that is why there's 2 binary variables on the left. And then if one of those is true, then okay, z equals 3, which does not occur anywhere else, has to have some flow as well. So that is why the constraint looks similar like this. And in the end, we have the sink, which has 4 incoming edges, and there has to be some flow there. We cannot just stop the process, right? Finally, there are some channeling constraints which say, okay, the aforementioned y equals 2, if it's true, then either this edge or the bottom edge has to have flow as well. And that completes our encoding. So to recap, we have our integer encoding. We can turn the integer table into a binary table and then apply the encoding. Or we can take that binary table and turn it into MDD, which can then be turned into these flow constraints, which can then be given to the solver. So these are essentially 3 different ways of encoding a table. So at this point, we can already run some experiments. So in the presentation, we'll be looking at the CSP instances from 2022 to 2025, all of them which have at least one table in them. We also ran experiments on the COP instances, and the results mostly carry over, but I refer to the paper for that. We use the Groby solver, latest version. We run it single core with some time limits and some memory limit. And we are mostly interested in the solve column. So for how many instances can we get a feasible solution? And the integer approach shows that the instances are quite hard because we only solve 55. For the Boolean approach by P, it solves 69. And then the MDD approach solves 67. However, the MDDs are notoriously sensitive to the way the columns are ordered. If you order them in a specific way, you might get a much smaller MDD. So if we have a domain, we tried a couple, and with the domain-based ordering is worked out well. So that solves even more. You can see, interestingly, on the constraint side that when we go from int to bool, the number of constraints goes up, but still you solve many more problems, which gives some credence to the idea that the binary variable are very useful. You can also see in the MDD that one has even more constraints, but the constraints are not all row. I don't have row number of terms in them like the int and bool constraints do. And you can see that the MDD DOM definitely saves a lot of constraints by considering a appropriate column ordering. So I should say that the encoding part has been mostly implemented by Wout Piesens. So if you catch him at CP and you have very in-depth questions, you can also talk to him. So this was, for me, really one side of the coin of how you can improve ILP solvers when we want to solve for table constraints. However, there's another path we can take here, because an ILP solver can do so much more than just this one-shot encode and solve that we have done so far. One advanced technique, which is known as logic-based pandas decomposition or row generation, and to which we will just refer as lazy cut generation, does not take this one-shot encoding approach. It's not eager, it's instead lazy. So I can explain how the algorithm works informally. There's 3 steps. First, we solve the problem without encoding any of the tables. And this will get us an assignment. Now, of course, unless we are extraordinarily lucky, this assignment is probably going to violate one of the tables. If it does so, then for that table, we generate a single cut, with which I just mean a linear constraint. And this cut has 2 important properties. The first property is that for it to be valid, it needs to violate the current assignment. And this will force the solver, once you restart it, to find a new solution, a new assignment. But on the other hand, the cut cannot violate the table constraint. This is, whenever you encode any constraint, you do not want your coding to violate the original constraint, of course. This is important to keep in mind. So these 2 properties is what we want. An example of a valid cut is the one you see here, because as you can see, we have x equals 2, y equals 2 plus z equals 2. And these are all set to 1. All the 3 terms are set to 1 by this assignment. So we will end up with 3 is less or equal to 2. So this cut definitely violates phi. However, 2 to 2 is not in the table. So it does not violate the table. Then we restart the process and we repeat this cut generation until we get an assignment which satisfies all the tables. Now the main challenge will be to create strong cuts, because the earlier example, this one, just removes this one solution. But that means we will have to add, well, it will remove at least one non-solution. It's a better way to think about it. Instead, we want cuts that remove many non-solutions at the same time, while never violating the table constraint. So there exists stronger cuts. For instance, this is an example that's only 2 terms and the right-hand side is lower by 1. So this will be a better cut. The question is, how do we find it? For this, we have a first algorithm. And I should note, for this first algorithm, we will just create cuts which are always have n terms and then less or equal to n minus 1. This means that there are logical clauses, if you prefer to think about it like that. So when we have this type of constraint, which has 2 terms, less or equal to 2 minus 1, 1, it actually says, okay, either x is not 2 or y is not 2. So our first algorithm for this is, we will say it's called the generate cut algorithm. It will work as follows. It will operate on the binary table once again. So here we can see it. And now we have this counterexample V, which is 2, 2, 2, this assignment, right? We will start from the empty cut, shown here. But the empty cut means that there are 0 terms in it. So we have 0 less or equal to -1. Now, the good news about the empty cut is that it violates V. The bad news of the empty cut is that it's also violating all the rows. So we're going to relax the empty cut by adding terms to the left-hand side, 1 by 1. And every time we do, we also increment the right-hand side. So we keep that n less or equal to n minus 1 form. And any term we add, we need to be careful that we are not suddenly no longer violating V. That means we can only add one of these 3 variables or columns. So the x equals 2 variable, the y equals 2, or the z equals 2, right? And it's these columns because they are assigned 1 by the assignment. So let's say I add one of them, let's say the x equals 2 variable, and then I increment the right-hand side. So now we're looking at x equals 2 is less or equal to 0. Then V is still violated because x equals 2 is set to 1 by V. So we'll have 1 is less or equal to 0. So that still fails, which is what we want. However, row 2, 3, and 4 have x equals 2 set to 0. So those are now suddenly allowed because they are no longer violated because 0 is less or equal to 0. We are still left with rows 1 and 5, which are still violated because x equals 2 is set to 1 there as well, just as it is in the assignment. However, now we can just pick another column, let's say y equals 2, and we pick that one because it has row 1 and 5 set to 0. So again, we add the y equals 2 to the cut. Now we have 2 terms, we increment the right-hand side, so it's less or equal to 1. And now V is still violated because that one would set both of these terms to 1. We would have 2 less or equal to 1. However, all the rows are now suddenly allowed, no longer violated. At this point, we are done, and we never had to add this third column or variable. The way we pick the columns is that we look at the ones which most quickly reduce the number of rows that we still have to allow by our cut. And this is, we have a straightforward heuristic for this. Interestingly, it does take, during cut generation, the most amount of time to generate because you have to basically read the whole, whatever is left of the table. So definitely go through all the rows for all the highlighted columns. Now, there are two extensions we also introduce, cut lift and fractional. And I will talk about both of them briefly, and we'll go a bit in depth about the cut lift. So cut lifting means that when we have a valid cut, we can strengthen it by lifting variables. With lifting variables, it just means we're going to add more variables to the left-hand side. However, we're not going to increment the right-hand side. So that one will stay fixed at 2 in this case. So consider this original cut that we have that has 3 variables less or equal to 2. We can strengthen it by adding a bunch more variables to it, as you can see here, while the right-hand side remains 2. And I will show you that we are still sure that this is a valid cut, as in that it still violates phi, but not any rows of the table. Now, the other part here is the fractional extension. In a MIP solver, it will, during the simplex algorithm, it will actually drop the integrality constraints on integer variables. So those 0, 1 integer variables might actually be assigned to 0.5 all of a sudden. And we can ask the solver to give us those solutions as well before it actually has to resolve the integrality constraints and get us a real integer solution, right? And we can save that work sometimes and get another cut like this, which already prevents the fractional solution. So I will mostly just explain the cut lifting approach. So we start from our valid cut, and now we're going to add variables to the left-hand side, but we're not going to change the right-hand side. What this means is that the constraint is only going to become stronger. And that is nice because we are then not worried about suddenly not violating phi anymore. If we make the constraint stronger, it's always going to still violate phi. However, we should be worried about suddenly violating one of the table rows. So we no longer have to look at phi, we can just look at the table. To ensure that we are not suddenly violating any of the rows, we introduce the concepts of tight rows and tight columns. Now, a tight row, such as row 2, it's one that assigns a variable such that the cut has no slack, in the sense of that the left-hand side is equal to the right-hand side. So row 2 is such a tight row, because if you have this cut here, then okay, x equals 3 is not in the cut, so that one doesn't matter, but y equals 2 is set to 1 by row 2. Z equals 2 is also set to 1. So we have 0 plus 1 is less or equal to 2. So this is a row we have to be particularly careful for, because it's at risk that if we, let's say, add x equals 3 to the cut, then now this row would be violated. So that's why we call row 2 a tight row, and I guess we'll call x equals 3, this column, a tight column, because it's set to 1 in any tight row. We should not only be careful for row 2, but also for row 5. Here you can see the cut. What would happen if we add x equals 3? We would violate row 2, because you would have 0 plus 1 plus 1 plus 1 is less or equal to 2. So 3 less or equal to 2. However, x equals 4, that one is fair game from the perspective of row 2, because it has a 0 right over here. And in fact, x equals 4 is 0 in all the tight rows. It's also 0 in row 5. It only has a 1 in row 3. And that one is not tight. So if we add x equals 4 to the left-hand side, that means that it has tightened row 3 a bit, but for the rest, nothing changed. In fact, row 3 is still not tight. We can lift x equals 4 again. So now we have 2 times x equals 4 added, but the cut is still valid. However, it has become stronger. And we can continue this process while there are still non-tight rows or columns left. So we can also add z equals 1 and x equals 1. And now we have much stronger constraints, again, in the sense that it removes more non-solutions. However, it is also still valid. So now, of course, we are curious how the cut generation fares against this one-shot encoding approach. So we run this on our CSP instances, and we can see that just generate by itself does quite poorly, only 36. We can see that the fractional actually does not change much. We can see that the cut lifting does help quite a bit. And if we put fractional and cut lift together, then it helps a bit more. So fractional does pay off when we also enable, when you do it in combination with cut lift. However, it's still only 55 solved, which is as good as the integer encoding. So that is, of course, a little bit disappointing because we did do a lot of work to get to this point. And we can look at this a bit more in depth by looking at the scatter plot like this. So scatter plot, it shows every instance as a dot here, and then it shows the solve times part 2 on the y and x axis. So all the dots that you see that are to the left and the top over here, they are better for the eager encodings, right? For the, in this case, we plot the MDD versus lazy cut generation with all the extensions on. So you can see that, let's say this is one instance, which is quite good for encoding. It solves a lot faster. They solve for both, but it's a lot faster for the encoding. And these are actually timeouts for the cut generation, but they are solved by encoding. And below the line and to the right, we see instances which are good for cut generation. So we can see it's not that it's always better to do encoding. It's just that it's more often better. But there are some instances for which the cut generation still works better. You can see that the colors, they actually indicate the number and the size of the tables. This is the sum of the rows of all the tables in the instance. So the yellow and the green, they are instances with very big tables in them. And then you can see that there is some correlation, at least, for that the cut generation works only if there are big tables, which is kind of the original motivation behind cut generation. What is it? What if a table is so big that you do not even cannot encode it, or even if you encode it, the solver will be overwhelmed by the number of constraints it takes to encode it. So this gives us quite a natural idea to hybridize the two approaches. Because what if we just make a cutoff at the number of rows, where we say, okay, tables that have fewer than, let's say, 1,000 rows, we encode directly, and all the tables which have more than 1,000 rows, we leave for the cut generation. Now, an instance will often have rows of different sizes. So then you have a truly hybrid approach in which some rows are encoded and some rows are left for cut generation. And for the instances which only have small tables, so that will probably be this cluster over here, it's equivalent to using just the encoding approach. So these are the final results for the CSP, where we tried, we look at this scatter plot to kind of figure out what are good parameters, and then we try a bunch of them, and we see that, okay, for 1,000 to 2,000, 3,000 rows, we actually get additional solved, and 2,000 seems to be the best. Then we get 4 additional solved over MDD-DOM. So this does show that, this brings me to the conclusion here that encoding still seems the most generalist and simpler approach. However, the cut generation can still help in specific cases. So in this work, we have studied, on the one hand, the eager encodings, and on the other hand, the lazy cuts for tackling table constraints. We have proposed the MDD-based encoding, which seems to work quite well and which outperforms the standard methods. We can also see that cut generation is definitely dependent on some extensions. You need to add the cut lifting and the fractional to actually get some improvement, to get something that is close to encoding. And finally, that there is a hybrid approach which is possible, which can take advantage of the complementarity of both paradigms. And in future work, we definitely want to understand better what table is good for encoding and what table is good for cut generation, because the number of rows is a very basic metric. There's more interesting methods to look at, for instance, the sparsity, or perhaps the size of the MDD that you would get from a table, which can be completely unrelated to the number of rows. However, this might be difficult to estimate without actually constructing the MDD. And then there are also many varieties of tables to which we can either do MDD encodings or cut generation, namely negative tables, which just list solutions which are not allowed, and smart tables where you can have wildcards, and also tables which are reified, so a table which is true only if and only if a certain other variable is true, or which are implied by another variable. And that brings me to the end of the presentation. So thank you very much for listening, and I welcome any questions.